let's do this. So we started talking about these carboxylic acid derivatives. We spent a bunch of time doing nomenclature last class, as well as doing our preparation of carboxylic acids. And now we're going to start talking about all the other ones. And what we're going to do is we're going to rank these in terms of their reactivity. So reactivity of carboxylic acid derivatives. All right. The first one, the most reactive, right? So we're going to start with most up at the top here. Are those acyl halides? All right, next up are those acid anhydrides. So that's when you have that oxygen sandwiched between two carbonyl groups. All right, we're going to throw a new one in here that we don't have to know the name of. I guess we don't have to know how to name nomenclature-wise. Let's just actually name these here. These are acyl halide, our acid anhydride. All right, and then this one is sort of analogous to an ester, but with a sulfur, what we call a thioester. All right, then we have our regular old ester. All right, and then last place here is going to be our amide. Okay? And what we're going to see, our amide is again our least reactive. All right, and what we're going to see is that we have the ability to convert those more reactive derivatives into less reactive derivatives. All right, so I can turn an acyl halide, that very most reactive carboxylic acid derivative, I can make it into any one of these other ones. If instead we start out with that acid anhydride, I can't make it into an acyl halide, but I can make it into everything else. Right? Etc., etc., etc. My thioester, what can I make that into? A regular ester and an amide. And if I have that regular ester, the only thing I can do with it is convert it into an amide. All right, so we can always convert something more reactive into something less reactive. All right, so why? Like, why the heck would that be? Okay? So first of all, notice that if I'm going to convert an acyl halide, for example, into an amide, I need to remove that chlorine and replace it with that nitrogen, right? So why is it going to be so much easier to take off this chlorine here than if I tried to go the reverse direction? What is it about chlorine versus nitrogen that we know that's going to make it easier to remove? What do we call that? It's a better leaving group, absolutely. So all this is ranking here of how good of a leaving group each one of these atoms are that's bound to that carbonyl carbon. So why? Because more reactive means a better leaving group. Now there's one carboxylic acid derivative here that I left off. And let's put this on here, but let's think, based on what we just discussed, where should the namesake of the group, the carboxylic acid, goes? It's actually tied with one of these other groups here, right? So where should this one go? What would be our leaving group? So the leaving group here, and we wouldn't have protonated, it would just be that OH minus, right? So that oxygen is our leaving group. So it's going to be tied with our other oxygen leaving group, our ester. Okay, these have the same reactivity. All right, and I can almost guarantee, mainly because I walked down that hallway and it smelled like banana oil, that you've done this conversion between these two before, all right? You can freely convert between a carboxylic acid and an ester. That equilibrium is incredibly well balanced, right? So dynamic that just by adding more alcohol, you push it in one direction, or by adding more water, you push it in the other direction, right? A very balanced equilibrium between the two, because again, the leaving groups are the same there. Okay? So we can always go from something more reactive to something less reactive. And again, what's sitting at the tippy top here are those acyl chlorides. Those are the best starting points for reactions because you can always turn them into something else. All right? So then how the heck do we make acyl chlorides? We do have one way to do it. All right? And that is, how do we go back? We can go back by starting with a carboxylic acid. But we're going to have to use something kind of fancy to do it. All right, so how do we prepare that thing that we can convert into anything? Our preparation. There we go. Okay, so this is going to use a familiar reagent. If we have, for example, a primary alcohol, what happens when we treat it with that thianyl chloride? All right, this was this really efficient way of replacing that hydroxyl group with a chlorine. And it turns out that if instead we were to take a carboxylic acid, and we treat it with that same fancy reagent, that same thianyl chloride, we get the same phenomenon, where that hydroxyl group is replaced with a chlorine. Okay, Okay, so this is kind of our one way of going back to the beginning here, is if we create a carboxylic acid, we can turn that into our acyl chloride using that thionyl chloride, SOCl2. Cool, all right, whoa. Work, there we go. All right, so how do we convert? So now this is kind of going to be the bulk of this chapter. How do we convert more to less reactive derivatives? Pause for dramatic effect. I don't know. Oh. Well, that's confusing. Okay. This is going to be fun. All right. Fingers crossed. So let's say that we want to go from our acyl chloride to one of those less reactive ones. Let's choose our carboxylic acid. All right. Well, what do we need to add in there? We just need to swap out what's attached to that carbonyl carbon. Okay? So if, for example, I just added in hydroxide, that would react with that carbonyl carbon. I would replace that chlorine, and that would give me my carboxylic acid. Okay? So what if I wanted to go let's do our acid anhydride. All right, and I wanted to make an ester. What am I going to add in there? I'm going to just look at what I'm substituting here. All right, so if I used that alkoxide ion, boom. All right, and we'll take a look at our mechanism here in a second. Oops. All right. Would this be under, if I was going to use this alkoxide ion, would I be acidic or basic conditions there? I'd have to use basic conditions, right? So this is just this ethanol, but under extremely basic conditions, giving me that alkoxide ion, all right? Let's take a look at our mechanism here. And I'm going to use this second example. We'll go back to our acyl chlorides. I'll just tell you right now, just kind of the punchline. We could absolutely treat an acyl chloride with hydroxide to get our carboxylic acid. Acyl chlorides turn out to be so reactive that you don't even need to use any sort of acidic or basic conditions. We could actually have just used water, all right? So we're going to kind of revisit acyl chlorides a little specially with our neutral nucleophiles. But let's just go here where it's real straightforward in terms of what we use as our nucleophile. And let's take a look at our reaction mechanism. So this is all right, so this is where we're going here. Let's see if we can't reason how we get from A to B on this one, okay? We obviously have two of these carbonyl groups on our reactant side, so I'm just going to say that this is the one that appears in my product here, just so we can kind of keep track of who's who. Now, given what we've discussed about carbonyl groups and reacting them with something like this alkoxide ion that has a ton of negative charge, what role do we think that carbonyl carbon is going to play? The what carbonyl carbon? The electrophilic carbonyl carbon. So just like we've seen over and over and over again, our nucleophilic alkoxide ion is going to come and attack that electrophilic carbonyl carbon. And what else am I going to have to do with this step? Can I stop here? No, what am I going to have to do? I'm going to have to kick that pair of electrons up onto that oxygen. I'll be good and include my lone pairs here, getting sloppy at the end of the semester. Cool. So then this is going to create our intermediate here. Still got that methyl group on that one side. That oxygen's accepted that pair of electrons, so it has this negative charge. I got my nucleophile attached at the bottom here. Cool, so here's my intermediate of the first step in this reaction mechanism. And we've seen this intermediate so many friggin' times that we gave it a special name. What did we name this intermediate? Our tetrahedral intermediate. And we trained ourselves to ask one question every time we see our tetrahedral intermediate, which was what? Do we have a good leaving group? And we're going to see that this is what makes our carboxylic acid derivatives different than our aldehydes and ketones, is because when we get to this point here, the answer to this question is what? Do we got a good leaving group in this molecule? Yes. So I got a whole bunch of oxygens. Let's label these A, B, and C. Which one is going to be my good leaving group here? B. And why is it B? Why is B different than C, for example? The carbonyl, right? And so what that's going to do is stabilize that negative charge through resonance. Okay, so let's just look at what I mean by that. If I bring down this pair of electrons and kick this guy off here, what is my leaving group for this reaction is going to be this oxygen with a negative charge. Not really a great leaving group, but what makes it so much better of a leaving group is that it's resonance stabilized. It's stabilized by that carbonyl carbon on the other side, right? So that's why acid anhydrides are sitting there at the tippy top of our reactivity list. Yes, they're below the acyl chlorides, but they're very close to the top because you have this resonance stabilized leaving group. Okay, actually that's it. That takes me all the way back here. Okay, so what we're going to see in our mechanisms kind of over and over again is the same thing we've seen with our reactions of aldehydes and ketones, where that carbonyl carbon plays the role of the electrophile. It gets attacked by a nucleophile, forming that tetrahedral intermediate. But then we get to that tetrahedral intermediate and we ask ourselves, is there a good leaving group? All right, and because this is a carboxylic acid derivative with an electronegative atom in that position, the answer is going to be yes. And so we kick off that leaving group. All right. For the sake of practice here, let's take another one. Our thioester. I want you to tell me how we should be converting this into a carboxylic acid. So to be clear, I'm going to look and I'm going to say, all right, I'm going to need this alkoxide ion. Nope, I'm going to need this hydroxide ion to play the role of the nucleophile. Boom. That gets me to my tetrahedral intermediate. We get to our tetrahedral intermediate and we ask ourselves, is there a good leaving group? Okay, so I think just by the implication of the problem, we get that this sulfide ion thing is going to be our leaving group. But why is that so much better of a leaving group than my hydroxide ion? Okay, again, because these are all ranked in terms of increasing, or rather, more reactive is a better leaving group, right? So why is sulfur a better leaving group? Why doesn't this just go right back in this direction here and kick off that hydroxide ion instead? So notice on the periodic table, sulfur is right below oxygen. Right? So that means that it's got very similar properties to oxygen, with one big exception: it's a lot larger. And the larger the atom is, the more happy it is to have negative charge. It can be more stable. So sulfur is just more stable bearing that negative charge than oxygen is. All right? Because it is a larger atom. So the other one we said was resonance stabilized. This one's a better leaving group because it's larger. All right, there's also an electronegativity component to this. Why is nitrogen a worse leaving group than oxygen? All right, oxygen's a little bit more stable with that negative charge because oxygen's more electronegative than nitrogen. All right, in general, nitrogen's pretty pissed off to have a negative charge. It's not like you never see it, but yeah, it's pretty furious. Okay, cool. So again, we do our nucleophilic attack. We say, all right, here's our tetrahedral intermediate. Is there a good leaving group? And we kick off that good leaving group. All right, so these are our substitutions from our more to our least reactive carboxylic acid derivatives. Cool. All right, so we talked about acyl chlorides. Those are the most reactive. Let's revisit those real quick because, again, they're kind of special. We kind of put them in a special category here. All right, and the big thing is that they are so reactive, we can use our weak, aka neutral, nucleophiles. All right, as we said before, this would certainly work. You could definitely take an acyl chloride and put it in a basic solution and you would get a carboxylic acid. But again, it's overkill. You could just put it in plain old water and you would get the exact same product. All right? And in this case, hydroxide's pretty cheap. That wouldn't be the biggest deal in the world. But like, you're definitely not going to go buy some alkoxide to make an ester with this sort of thing, right? You're just going to use your cheap alcohol to do it. So for our acyl chlorides, we're not going to go crazy and use those special nucleophiles. We're just going to use our neutral, our weak nucleophiles in order to do these conversions. All right, so let's see if we can't figure out our mechanism here. To create our carboxylic acid using just regular old H2O. Right? What we're going to see here is we have very similar mechanism, except now we got one problem, which is we don't have our carboxylic acid. but we have this protonated carboxylic acid. All right, so what do we think the last step is going to have to be? What are we going to need to have in this mechanism? Yep, proton transfer, right? So we just need some base to accept that, okay? So this is maybe going to be kind of the biggest pain here is what base do we use? In this case, we have a bunch of these water molecules floating around, so they're perfect to play the role of that base. All right, and so notice that one of your byproducts in this reaction here is going to be that hydronium ion. All right, and so this reaction here will create this acidic solution, right? You're necessarily creating this abundance of protons here by carrying out these reactions under neutral conditions. Okay? So, let's just do another example real quick. All right, we want this to be, let's just do a methyl ester here. All right, so what nucleophile should I use? Am I going to use an alkoxide ion, a methoxide ion? No, that'd be way too expensive, unnecessary. I can just add in methanol. Okay? But let's just note here that if we were doing our balanced chemical equation, our other product here would be what? If we're keeping track of all of our atoms, right? On my product side, I'm going to need to add one additional hydrogen and one additional chlorine. So in my balanced chemical equation here, I've got this HCl product. Okay? Now, is the chloride ion actually going to be doing the accepting of the proton, or is the alcohol itself? There's going to be a mix of both in there because neither of them are great proton acceptors, all right? But for the sake of keeping a balanced chemical equation, we're going to let that chloride ion be our proton acceptor in these mechanisms here, right? So that at the end of the day, we get our HCl product at the end. Okay, so everybody take a second, see if you can't finish off this mechanism based on what we just said. We're going to let this be our proton acceptor at that last step. Okay, so again, what we're going to say is at the last step, in order to get our balanced chemical equation here, we're going to let that chloride ion play the role of our base, which is, again, a little iffy. Chloride's not a good base, but neither is methanol. All right, so something sun there is going to accept that proton. Really, everything's going to be passing it around because nobody really wants to have it. But for the sake of argument and making our balanced chemical equation, that's what we're going to do. Okay? There's going to be one big exception here, and that is if we want to convert this same acyl chloride into an amide. Okay, if I want to convert this same acyl chloride into an amide, what nucleophile am I going to use? Nitrogen, and then it's going to give it an extra proton, so what do we call NH3? Ammonia. All right, we're going to have our same nucleophilic attack here of that electrophilic carbonyl carbon. Get our same tetrahedral intermediate. Okay, we'll kick off that good leaving group, that chloride. And previously we were kind of quibbling over the base that we should use, and it's like, methanol, chloride, they're both kind of crappy bases. We're just, for the sake of argument, going to say chloride for our balanced chemical equation. We don't have that same problem here, because there is a dang good base floating around in solution right here, right? And that is our nitrogen nucleophiles. Remember, nitrogens are themselves weak bases. So importantly, what's going to happen in this reaction is nitrogen's going to play the role not only of a nucleophile, but also of a base. All right? And this is so true to the point where if you were going to carry out this reaction, you could not do so with just 1 molar equivalent of amine, because half of it would be used as a nucleophile and the other half would be mopped up as a base. So what you see in our reaction substrate reagent product combinations here is that we're going to have to specify that we use 2 equivalents of whatever amine it is in order to get this reaction to proceed to completion here. All right, and again, to be clear, that's because one of those equivalents will play the role of the nucleophile, whereas the other equivalent will play the role of the base. Okay? All right, so now we need to focus. We talked about going from more to less reactive, and then we took a bunch of time to sort of specify this most reactive bracket here. Now we're going to kind of focus on this one here. this tier where these two are sitting at the same level. Okay? We can convert between a carboxylic acid and an ester pretty freely, and this is what's called a Fischer esterification. And I think the name is a little bit misleading because really you can go the other way as well, just as easily, okay? But importantly, these are reactions that are catalyzed under acidic conditions. When you made that banana oil, you mixed your carboxylic acid, your alcohol, and a bunch of acid in there, and that's what created your ester product, okay? So our Fischer esterification, this is the conversion of a carboxylic acid to an ester, or vice versa, under acidic conditions. So let's do your banana oil lab. We're going to take this acetic acid. We're going to mix in isopentyl alcohol. All right, but again, we're going to carry this out under acidic conditions. We're going to get that fake banana-y smell. Okay? And usually in organic chemistry, we're real lazy and we don't bother to include our inorganic product. But what's going to be the inorganic product of this reaction? We need it to survive. Water. All right, and important this, and why I want to make this distinction, why I'm going to include this, is because again, this reaction is 100% reversible, meaning that if instead I combined my ester and water under acidic conditions, it would push the reaction in this direction. Okay, that's why you went out of your way to do those drying steps when you made that banana oil as well. All right, so a carboxylic acid, unlike our acyl chloride, cannot react with this weak nucleophile as is, right? It's just not good enough of an electrophile. So what we're going to do is this common sort of trick that we've used to turn these carbonyl carbons into even better electrophiles under acidic conditions, which is to protonate them. All right, so the very first step here is not going to be nucleophilic attack. Our nucleophile is too weak. We're instead going to, again, real lazy with these lone pairs. All right, we're instead going to protonate that carbonyl oxygen. All right, and this will turn our nucleophile, or rather our electrophile, into an even better electrophile. Okay. I want you to take a second and see if you can't figure out the rest of this mechanism. I'll sort of quietly fill it in up here so you can check your work. But from here on out, it is very, very similar to what we've done up until this point. I will say that you are under acidic conditions, meaning there's a ton of also water molecules floating around that are free to play the role of the base here in this reaction, as we can see from our products. Oh, I guess not. We'll reform our catalyst rather. Okay, I'm hoping everybody got to this point here, right? Our tetrahedral intermediate. And what are we going to do when we see our tetrahedral intermediate? Do we have a good leaving group? Okay, so A, B, C. We kind of have a problem here. What is the good leaving group in this tetrahedral intermediate? Right? What's the only thing that's going to leave as a neutral molecule? B. B is my good leaving group here, right? Because it's got that positive charge. Well, if we kick off B, please go right back to the beginning. Fantastic. We did absolutely nothing, right? So B is the good leaving group here. We have a problem. We can't just kick off something else because B is our good leaving group. So what do we need to do? We need to do what we had to do before to manage our charges. And I guess to be clear, I can't just go ahead and kick off this hydroxide ion. First of all, it's not the best leaving group. Second of all, I've violated my acidic conditions, right? So how do we do our charge management? Proton transfer, all right? And we can do this the lazy man's way. I'm going to need to deprotonate B and protonate. It actually doesn't matter if it's A or C, but let's just say C. Let's just go ahead and do an intermolecular one here to change that proton onto our leaving group. And to be clear, there will be a bunch of like back reaction at this step where B gets kicked off, but that's not your productive step forward, right? So the only way to do a productive step forward is to have a proton transfer to make that better leaving group. All right, and so we are out of time. From here, I trust that y'all can then do one last proton transfer to deprotonate that carbonyl carbon using just water. And that would reform our acid catalyst. All right, so the big difference here is in this Fischer esterification, we get our tetrahedral intermediate, but then within that tetrahedral intermediate, we have to do a proton transfer so we don't kick off the thing that we just started with, right? So we don't wind up right back at the beginning. Cool. All right, I'll leave this up for a minute. Y'all got one more lecture and new material. Hang in there.